Hello everyone and welcome back to the channel. So this time we are going to do an A2 past paper video. So A level or the second year of A level, that's called A2, and we are doing the most recent paper that we have as of now, which is the Feb March 2025 paper, and there's only one variant, which is the 4.2 paper in this series. Let's get right into it. To save time, I've already solved this beforehand and I'll be going over the reasoning in more detail, because otherwise this is a 2-hour paper and the video would be really long. So let's start with question number 1. So with this, after a lot of time, again we had an appearance of just a circular motion question. So this says a steel ball is placed on the inside surface of a hollow circular cone. The ball moves in a horizontal circle at constant speed, right? The angle of the side of the cone to the horizontal is 52 degrees. There is no friction between the ball and the cone. 1.2 shows a cross section through the cone and the steel ball. And basically what you had to label in this part is the forces acting on this. So obviously there is the reaction force here, and then there's the weight. Weight is downwards, reaction force is perpendicular to the surface. In part B, it says describe how the forces acting on the ball causes its acceleration to be centripetal. This is a very common question which is asked again and again. It's asked in gravitation, it's asked in the chapter of magnetism as well. So it's asked, how does it cause the acceleration to be centripetal? Another type of question, which would also mean exactly the same thing, is that if it would say that describe how it is in circular motion. So the idea is that for circular motion, there needs to be a resultant force towards the center. If I resolve this into components, I know that if this is 52, so this is 52, and then this would be 90 minus 52. And then again, because this is 90, so this would be 90 minus 52, 90 minus 52. So this would again be 52, right? So this and this angle are the same. So if this is 52, then this component with the angle is the cos one, this one is the sine component. So I can say that the cos component, the vertical component of the reaction force, equals the weight. So there is no resultant force in the vertical direction, but there is nothing countering this component, which is towards the center. So there's the force towards the center, which also produces an acceleration towards the center. That is what I've written here. In the next part, it says that the ball moves in a circle of radius 0.15 meters. Show that the speed of the ball is this much. So obviously I can't use anything like V equals R omega or something, because I just know how the forces are. And I literally don't know anything except that. I don't know the mass. I don't know anything. All I know is this angle. So if I think about the forces, I would say that W equals R cos 52. And the centripetal force is provided by this resultant towards the center. With this, I'd get two equations. So the centripetal force is R sine 52 and the weight is equal to R cos 52. The centripetal force I can write as mv square over R or mr omega square. Both of these are really commonly used. Because I need the speed of the ball, so I'll use the expression which contains speed, which is mv square over R, right? So when I have these, I can see that by dividing these, I can get rid of R, which I don't know anyway. So this simplifies stuff. So there's mv square over R divided by weight, which is mg. M's cancel again. So this becomes v square over rg equals tan 52, right? So the trigonometric identity that sine over cos is tan. And then from here, I need v, right? So that becomes the root of rg tan 52. R is this, G is 9.81, tan 52. This turns out to be 1.4 meter per second to 2SF. Then it says calculate the angular speed of the ball. So obviously we use V equals R omega. I need omega, so that would just be V over R. And that turns out to be 9.1 radians per second. In part E, it says the speed of the ball is increased. Explain why the radius also increases. So now I can think about this equation that circular centripetal acceleration is given by v square over r, or if you want to, you can also think about the centripetal force, which is mv square over r. In any way, I can say that because the centripetal acceleration is the same, So V square is proportional to R. So if V increases, then R would also increase, right? So since the resultant force, or you can say the centripetal force or the centripetal acceleration is the same, so radius is proportional to the square of the speed, which you can see here as well, right? So V square equals Fc over m times R. This is a constant, this is a constant. So V square is proportional to R. So if speed increases, radius also increases. Question number 2. The magnitude of the gravitational potential on the surface of a planet of radius r is phi. The planet can be considered to be an isolated sphere. On 2.1, sketch the variation of the gravitational potential with distance x from the center of the planet for values between r and 4r. So I know that gravitational potential outside is given by this expression minus gm over r. And if you've seen questions like these, then you know that this is on when you have this graph, so you'll also have coordinates labeled. So phi is basically inversely proportional to r. And inside this sphere, because there's no work done, so phi is constant, right? So this is the idea. So phi would be constant inside at negative phi, and then it follows the inverse square pattern. So if at the radius r, at a separation of r, if the gravitational potential is phi, when the separation doubles, the phi value halves. And then similarly, when the separation doubles again, so if it becomes 4 times the value, then this becomes 1 over 4 times the value. So that's this coordinate, which is minus 0.25 comma 4r comma minus 0.25 phi. And if you want to, you can also look at this with 3r. So with 3r, when the separation triples, this becomes 1 over third of its value, which is 0.11, right? So that's how you sketch this. A satellite is in a geostationary orbit above the Earth. Now this is a new part. At time t equals to 0, the magnitude of the gravitational potential due to the Earth at the location of the satellite is phi. On 2.2, sketch the variation of the gravitational potential due to the Earth at the location of the satellite for values of t between 0 and 24 hours. Okay, so a geostationary orbit, what does that mean? We have some conditions for it. What a geostationary orbit basically is that when we look at this from the Earth, it appears in the same position always. So it's at a fixed distance from the Earth always. It has the same direction of rotation as the Earth. It has the same time period as the Earth, and it's in an equatorial orbit. Now in this case, when we have to sketch the variation of the gravitational potential due to the Earth at the location of the satellite, so we'll use this idea that, all right, phi equals minus gm over r, right? But this time we are looking at the potential at a fixed radius. It's always the same. So this time phi would not actually vary at all, and it's just going to be constant at this negative phi value, right? So if the magnitude is phi, we know that gravitational potential is always negative. So I draw a horizontal line at negative phi, right? So because it's a geostationary orbit, distance from the Earth is the same, so r is the same. So this is a constant valued graph. Part C, electric potential between two parallel plates is shown. Distance between the plates is d. Region between the plates is a vacuum. On 2.4, sketch the variation of the electric potential with distance from the positive plate. So we know that between parallel plates, electric field strength is constant. Now, if we have a VD graph, that means that its gradient is going to be constant. And I basically use this property that E equals negative of the potential gradient, right? So it starts from here. So it says sketch the variation of electric potential with distance from the positive plate. At the positive plate, it's positive V. And then at the other plate, after I've moved through this distance d, it's going to be 0. So this is a graph that goes like this. Starts from V and at distance d from the positive plate. So when I'm at the other plate, the earthed plate, so the potential is 0. Question number 3 now. Two metal cuboids P and Q are in thermal contact with each other. P and Q are in thermal equilibrium. What is meant by thermal equilibrium? Very textbook definition. So they have the same temperature. So in essence, there is no overall or net thermal energy transfer. Data for P and Q are given in table 3.1. P and Q are initially both at the same temperature. So they're in thermal equilibrium initially. P is supplied with 24 kilojoules of thermal energy. After some time, P and Q are once again both at the same temperature. So they reach thermal equilibrium again. Now, how would that happen? Because they're perfectly insulated from the surroundings, is that even if P gets this energy is basically shared between both of them, right? So if P has an excess, P would give some of its energy to Q, and this would keep happening until they are in thermal equilibrium. So I have specific heat capacity given, I have mass given, so I know that this 24 kilojoules of energy would be shared between the two. So I can say that again, we need to find the change in temperature, and because they started at the same temperature, and again they're both in thermal equilibrium and they have the same temperature, right? So thermal equilibrium means same temperature. So they had the same temperature initially, they have the same temperature finally. So for both of these, the change in temperature is the same. And I know this equation Q equals to mc delta T. So I'll say that 24,000, which is 24 kilojoules, is the energy supplied to P plus the energy supplied to Q. So I write the mc delta T equations for both. So for P, mass is 0.54, C is 390, and delta T, the rise in temperature. And similarly for Q, so 0.37, 910, and delta T. Then this is just algebra. You will solve for delta T, which turns out to be 44 Kelvin. Next part, it says nitrogen may be assumed to be an ideal gas. A fixed amount of nitrogen gas is contained at a constant pressure of 1.6 into 10 to the 5 pascals. Variation of the volume of the gas with temperature theta of the gas is shown in 3.1. Also, intuitively, that makes sense why the graph is like this. So we know that for an ideal gas, V is proportional to T, but that T is thermodynamic temperature, which means it's in Kelvin, right? So if this was a graph of temperature in Kelvin, then this would be a straight line through the origin. But because this is in degrees Celsius, so this is not passing through the origin. I know that absolute 0 Kelvin is minus 273 degrees Celsius, which means that if I take this graph back, then where it would intersect this axis, the horizontal axis, this would be at negative 273, right? So I've drawn this by mistake, but like if this is your axis, you take it back. So the x-intercept would be minus 273, which is the same thing as 0 Kelvin. So minus 273.15 degrees Celsius is 0 Kelvin. So it says temperature of the nitrogen gas is increased from 0 to 210. So this is 0 and this is 210. And you have to find the work done on the gas. Now, if you're thinking about this, and you should be thinking about this in terms of thermodynamics, the first law of thermodynamics. So you know that here the gas is expanding. How I visualize this is that the gas is pushing back against the piston. So if it's pushing against the piston, the gas is doing work. So work is really done by the gas. And the question is asking for work done on the gas. So I can find the magnitude very easily because I know the pressure. Using these read-offs, I can get the change in volume, right? Which seems like 0.32. So 0.32 minus 0.18, that's a change in volume multiplied by the pressure. But because this is work done by the gas in reality, and the question is asking for work done on the gas, this would be negative, right? Because in reality, work is done by the gas, not on the gas, right? So the minus sign you are basically using to show the examiner that the question you've asked is wrong. Determine the number n of molecules of nitrogen gas. So it's an ideal gas. Always underline this with a pencil whenever you're doing this question. So you need n, so you can use this equation, PV equals nKT. You need n, so that's PV over KT. You can pick up any certain value of volume and temperature. Let's say I pick up this one. So volume is 0.32, temperature was 210, but that was in degrees Celsius. Whenever you use ideal gas equations, make sure your temperature is in, what do you call it? Kelvin. So I used the zero value actually. So 0.18 is this one, the temperature is 0 degrees Celsius, which is 273 Kelvin. And then I just plug this in and multiply. So N turns out to be 7.6 into 10 to the 24 number of molecules. Mass of a nitrogen molecule is this much. Calculate the RMS speed of a nitrogen molecule at 210. So I know that internal energy is given by this. You need to remember this expression 3 by 2 kT, and you also need to know how this is derived. So 3 by 2 kT is equal to half mc square. Halves cancel out, right? So halves cancel out, so I need c square, which is the mean square speed. So I'll also need to take the root after rearranging. So that's the root of 3 kT over m. Again, just plugging in values. 210, so I add 273 to convert this to Kelvin. Divide by the mass of one molecule to get the RMS speed. That was this question. Question number 4. A small crystal is made to vibrate with SHM. Variation with time of displacement of the crystal from its equilibrium position is shown in 4.1. Show that the angular frequency is given by this. So I can look at the time period here, which is 0.15 seconds, and angular frequency is basically omega. So omega is 2 pi over t. You just plug in values, and this is the answer you get. Max acceleration. So max velocity is given by x naught omega. Max acceleration is given by x naught squared omega, right? Or you can say omega x naught squared. So I have omega already found out. This is the amplitude, which is 40 into 10 to the negative 6. So 40 into 10 to the negative 6 into 4.18 into 10 to the 10 square. Oh, I made a mistake in saying this. It's not x naught square omega, it's x naught omega square. So you just plug in these values, and this is the answer for acceleration that you get. Crystal may be modeled as a single mass of this much that vibrates as shown. Calculate total energy. This is another expression that you need to know. Half m omega square x naught squared. You have everything you need. You have the mass, you have omega x naught. So you just plug the values in here, and this is the answer that you get for this part. The crystal generates ultrasound waves that are used to obtain diagnostic information about internal structures. Crystal is made from piezoelectric material. Explain how the crystal is made to vibrate. So this is talking about the production of ultrasound. So what we do is we apply an alternating PD. This causes the crystal to deform, and when it does deform, it sends out these waves, the frequencies of which lie in the ultrasound range. A parallel beam of ultrasound waves is incident on a muscle-bone boundary. Data for muscle and bone are given. Calculate percentage of intensity that is transmitted at this boundary. So we know of something called the intensity reflection coefficient, which is alpha, which is given by this expression, z2 minus z1 square over z2 plus z1 squared. So I'll need to calculate the z values for each of these, and z is calculated using rho c. So rho multiplied by c, rho multiplied by c. I'll get each of the z values, but remember that alpha tells you how much intensity is reflected, right? It tells you how much of the incident intensity is reflected. So let's say if alpha turns out to be 0.9, this means 90% is reflected, so 10% is transmitted. So I found out ZmZb using the rho c equation, and plugging in the values here, alpha turns out to be 0.4, which means 40% is reflected. So 100 minus 40, 60% is transmitted through. Let's go on. A capacitor of capacitance C1 is connected in series with a second capacitor of capacitance C2. Show that combined capacitance is given by this. So with series, voltage is split, and just like we used to say in AS, current is the same, we say charge is the same. So V equals V1 plus V2, C equals to Q over V. So this becomes Q over V equals Q over V1 plus Q over V2. If I factor out the Q's, all of these cancel out, giving me this. Oh, I wrote this incorrectly. Since C equals Q over V, so V equals Q over C. So this is Q over C equals Q over C1 plus Q over C2, right? And then you just rearrange this. Three identical capacitors, each of capacitance C, are connected in the network as shown in 5.1. Variation of charge Q with potential difference between the terminals is shown. So it's the total charge and the total potential difference between these terminals. So first of all, I can see that both of these are in series with one another. So the net capacitance would become C by 2 here. And this is in parallel with this. So this would become C by 2 plus C, right? And 1.5 C would be the total capacitance here. Anyway, going on with the question, variation of the charge with potential difference is given. So you have a QV graph, Q is in microcoulombs. I also know that because C equals Q over V, so the gradient of this graph would basically be capacitance. But again, this is the total capacitance here, which was 1.5 C. And this is what you have to use in this part that show that C equals to 44 microfarad. So first I found the net, the total capacitance, which is C by 2 plus C, which is 1.5 C. Total capacitance is given by Q over V. So I pick up this value, 400 micro over 6 volts. That is the total capacitance value, and that is equal to 1.5 times the value of one capacitor, which is C. And then I just rearrange to find C. Capacitor network is charged and then connected to a resistor of resistance 54 kilo ohms. So then the capacitor discharges. Determine the time constant. So the capacitor, the entire network is charged, and it's then connected to the resistance of 54 kilo ohm. So determine the time constant of the circuit. Give a unit with your answer. So for this, you just use tau equals to RC, right? That's the value for the time constant. So you just multiply the two. Oh, I also made a mistake here, which is that this value is of the capacitor network, right? And this is the value of 1. So this would also be multiplied by 1.5. And then when you do this, this answer turns out to be 3.6 seconds, right? Pretty easy, just plugging in the values. Then determine the time taken for the discharge current to reduce to 15% of the initial discharge current. So I know that charge, current, voltage all follow this exponential decay. E equals to negative T over RC. So for it to become 15% of initial, so if the initial is I naught, so I'm waiting for it to become 0.15 I naught. RC is basically tau, so I plug in 3.6 here. I naughts get cancelled out. I take ln, so ln 0.15 becomes ln of this thing. So ln E disappears and this power comes down and multiplies, which is minus T over 3.6. And from this, I just basically find ln 0.15, multiply this by negative 3.6. So the time turns out to be 6.8 seconds. 6. An electric field and a magnetic field are used to form a velocity selector. Charged particles called ions pass into a region of uniform electric and magnetic fields that is between parallel plates as shown in 6.1. Right, so you have your, let me first remove this. So you have your positive plate, you have your negative plate, you know, electric field lines are like this. And you have your path of ions. So with the velocity selector, it basically goes through undeviated. So the potential difference is given, separation of plates is D, magnetic flux density is B. Show that speed U of the ions that pass through undeviated is given by this. If they are undeviated, then however the ions, there's some electric force when it enters this electric field. And that electric force must be equal to the magnetic force for it to pass through undeviated, for it to not deviate at all. So I can use this idea that the magnetic force equals the electric force. The magnetic force expression that we use for charged particles is BQV. So BQV equals to, I can say, EQ. Electric field strength is the force acting per unit charge. So I multiply this by the charge. And because this is a case of a uniform field, so instead of E, I can write V over D. So Q's cancel out. I need U as the subject, right? So instead of BQV, I wrote BQU because that's the symbol the examiner uses. And I just make that the subject. So U equals V over BD. Positive ions with kinetic energy this much, mass this much, pass undeviated when V equals to 980 and small d equals to this. So first of all, I can see that with the kinetic energy expression, I'll need first the velocity, which I can calculate. That's very straightforward. And once I have that, I need B. So B would become equal to V over UD, and then I'll just plug that in, right? So that's shown here. So first I find U using the kinetic energy equation rearranged. That turns out to be 1.6 into 10 to the 5 meter per second. And then I plug that into here. So V over UD, and this is what it turns out to be. 0.17 Tesla. A proton passes undeviated through the velocity selector. An alpha particle enters the velocity selector at the same speed as the proton. State how the expression in A predicts that the alpha particle is also undeviated. So how do I see that is because this expression that you have, that you just derived, you don't see the mass or the charge anywhere here. For a proton, I know the charge would be positive E, right? So 1.6 into 10 to the negative 19. For an alpha particle, it would be positive 2E. Similarly, the mass of an alpha particle would be 4U, whereas the mass for a proton is just U. So because I do not see mass or charge anywhere in this expression, I know it doesn't depend on mass or charge. It just depends on speed and the voltage and the magnetic flux density and the distance, right? So it doesn't depend on anything else. So that's the idea here. By reference to 6.1 and to the forces acting on a positive ion, determine the direction of the magnetic field, explain your reasoning. So if you're talking about positive ions, so I know that positive ions would be deflected like this, attracted to the negative plate. And you can also think about this in terms of the field lines, which would be positive to negative, and field lines just show the direction of force on a positive charge. So if I know that the electric force is downwards, then magnetic force would be upwards. And now I must use Fleming's left hand rule. So the thumb of my left hand points upwards. These are positively charged ions, right? So how they're moving is also the direction of the current. So then what I see is that my index finger points into the page. So this means that the direction of the field in this case would be into the page. So that's also what's written here. If the electric force is downwards, so for it to pass through undeviated, magnetic force must be upwards. Current is from left to right, exactly how these positively charged particles are moving. And by Fleming's left hand rule, the field is into the page, right? Then it says the positive ions in B enter the velocity selector with a greater kinetic energy, right? So now they have a greater kinetic energy, so they have a greater velocity. Now, if they have a greater velocity, then both of these, which were previously equal, will now no longer be equal. This has velocity, velocity goes up, so the magnetic force goes up. And magnetic force was upwards, so now it deflects upwards like this. So that's the reasoning behind this part. Let's go on. Faraday's law of EM induction, very straightforward. Induced EMF is proportional to rate of change of magnetic flux linkage. A metal rod is accelerated uniformly from rest in a uniform magnetic field as shown in 7.1. So this rod goes like this in a field which is into the page. And this is the direction of acceleration by Newton's second law. I know that this is also the direction of the force acting. The rod has length L, flux density is B, and EMF is induced in the rod. right? Makes sense because it would be cutting through field lines, and the variation with time of the induced EMF is shown. So the induced EMF is basically, you can see it's directly proportional to time, so it's linearly increasing. It says, explain how 7.2 shows that E is proportional to V. How is E proportional to V? So I was told that it's uniformly accelerating. So if it's uniformly accelerating, then I can say that, all right, if it's uniformly accelerating and this was from rest, right? Initial velocity is 0. So I can say that, all right, then the velocity is basically proportional to time. Because of this expression, A equals V minus U over T, right? U is 0. So V equals to AT. So V is proportional to T. And the graph tells me that E is also proportional to T. So if I eliminate the E's, I can say that E is proportional to V. Now look at how I've explained this. So the graph shows that EMF is proportional to T, right? So this is a typical direct proportionality graph, a straight upward sloping line through the origin. And since acceleration is uniform, velocity is proportional to time, right? So I've just explained this. Use Faraday's laws to show that the variation of E with time is given by E equals to BLAT, right? So BLAT. B is the magnetic flux density, L is the length of the rod, A was acceleration, and T is some time. So I know that E is, by Faraday's law, given by this expression, minus n delta phi over delta T, right? By a combination of Faraday's and Lenz's law. But I know that there is no, what do you call it? There's no turns here, there's no coil, so there's not really magnetic flux linkage, it's just magnetic flux. So it's, if I'm talking about the magnitude, that's delta phi over delta T, and I know that phi equals to BA. So I say that, all right, E equals to delta phi over delta T, and phi is BA. B is constant, so I can take this outside of the delta, so it's not changing. So it's B into delta A over delta T. I can say that this area and how much it's changing is basically its length, and let's say it goes from here to here. This is its breadth. So delta LB over delta T. Now how do I find breadth? So I can say that the breadth that it covers is basically the velocity multiplied by delta T, right? So in some time, how much distance it covers is V delta T, right? So that's the next thing I've written. So again, L was also constant. I can take this outside, so this becomes BL into delta small b, which is the breadth, over delta T. And instead of delta B, I can write V delta T over delta T. So this becomes BLV, and as I just wrote that in some time T, because it started from rest, so V was just equal to AT, right? V is just equal to AT. So instead of V, then I write AT to get my desired expression. Next, length of the rod is given, acceleration is given, and you have to find B. So this is just a matter of plugging in values, not very difficult. That ends this question. 8. State what is meant by a photon, very textbook definition, a packet or a quantum of energy of electromagnetic radiation. Please write out the full words. I've just written it like this to save time. A laser light emits red light of wavelength, of a single wavelength. Light is produced when electrons move from a higher energy level to a lower energy level. So they de-excite basically, and they emit photons. And the difference in energy levels is this much, so I know that the energy of the photon emitted is also this much. And I need the wavelength, so E equals HF, but in terms of wavelengths, E equals to HC over lambda, because lambda is what I need. So lambda equals to HC over E, but keep in mind that you'd also have to convert this energy to electron, from electron volt to joule, so you just multiply this by 1.6 into 10 to the negative 19. So H is Planck constant, C is speed of light, lambda is, so I've rearranged this, right? So lambda equals hc over E, so 1.96, and to convert this to joules, I multiply by the charge of an electron. Wavelength turns out to be 6.3 into 10 to the negative 7 meters. Power of beam emitted by the laser is this much. Calculate the number of photons emitted per unit time by the laser. I think that questions like this, it's better if you just use the unitary method as far as you can, because this is basically the energy of one photon, right? 1.96 into 10 to the negative 19, that's the energy of one photon. So the total energy per second, and that's all what I also need, the number of photons per second. So energy per second, or the power, is given. So if this is the power of like n photons, so what are the number of photons? So that's the total power or the total energy divided by the energy of one photon. So that is 3.2 into 10 to the 16 photons coming in at the surface per second. Photons are incident normally on a surface. Half of the number of photons are absorbed and half are reflected. Determine the average force exerted by the beam of photons on the surface. If you've been doing quantum physics past papers from the recent years, you know that the examiner is asking questions like these very often. So force, in this case, you have to use that's equal to the rate of change of momentum. So F equals to delta P over delta T. And for P, you have to use this equation, that P equals to E over C, right? So energy is given and C is the speed of light. So the momentum of these turns out to be this value, 1.045 into 10 to the negative 27 kg meters per second. Now, when we talk about the change in momentum, we say that half of these are absorbed and half of these are reflected, right? So when I find the change in momentum, basically half of these are absorbed, half of these are reflected. Now for the ones which are just absorbed, this means that they had some initial momentum, which I've just calculated here, and then finally there's no momentum, right? But for the ones that do reflect, that means that they have this momentum and they also come back with the same momentum. For these, the change in momentum would be 2p because of the sign convention, right? If one of these, let's say to the right is positive, to the left it's negative, so this would become minus p, final momentum is minus p, minus the initial momentum, which is just p. So the magnitude becomes 2p. So that's when you do this. Now if you have halves here, and why do we have the halves? Because of this information. So the halves can be factored out, which I've done here. So 0.5 delta P of the absorbed ones is just equal to the initial momentum. For the ones which are reflected, it's twice of the initial momentum, and you have to divide by the time. Another way to think about this is that this is for basically one photon, right? This is the change in momentum of one photon. You multiply, sorry, this is the force for one photon, and you multiply by the number of photons, so you get the average force which is exerted. So this was also a very technical question. 9. So polonium is an unstable nucleus. It decays to a nucleus of this much by emitting alpha. Radioactive decay is both random and spontaneous. State what is meant by these. Again, very textbook. Random, impossible to predict when a certain nucleus will decay, or you can say which nucleus will decay. And spontaneous means it's unaffected by external factors. Half-life, so time taken for the number of undecayed nuclei to half, or you can say the time taken for the activity of the sample to half. Even though this was acceptable in O levels, you can't say time taken for count rate to half. The examiner will not accept this. Data for binding energy per nucleon number is given in electron volt. Determine the energy in electron volt released when a nucleus of polonium decays into a nucleus of lead 189, and above it was said that it was using alpha decay. So this is basically your reactant here. You can say this is like initially what's there, and this is what's finally there. So you just add these, but this is binding energy per nucleon, so you'd also need to multiply by the nucleon numbers here. So then you have your binding energies, the difference between that tells you the energy released. So 189 times this, 4 times this, I've added both of these, minus 193 times this. So that gives you 7.03 electron volts. Pure sample of polonium contains N naught nuclei. After a time t, the sample contains N nuclei of polonium. The variation of ln N over N naught is shown. So pretty much like some capacitor questions, if you remember seeing those. You also have ln graphs in this, and this is a good time to start thinking about why or what this graph shows. So I know that generally it's radioactive decay, so it's exponential decay. So n equals to n naught e to the negative lambda t. Again, I take ln's. So ln n over n naught equals minus lambda t. This is basically what's on my y-axis. Time is what's on my x-axis. So the gradient is negative lambda. Right? This is stuff you should be doing as you go along. This should be naturally coming to you, because believe me, it will be tested in the later parts, and then you won't be taken by surprise by the question. So it says, and now look at this, state the name of the quantity that is represented by the magnitude of the gradient. So gradient is minus decay constant, so the magnitude is just the decay constant. Use 9.1 to determine the half-life. So once I have the gradient, I can find the decay constant. I pick up this value, which is on the y-axis, it's 1.4, on the x-axis, this is 0.8 millisecond. Right? So 1.4 over 0.8 millisecond basically gives me the decay constant, which is 1750. Then I use this equation that lambda t half equals ln2. So I rearrange. So t half, which is the half-life, is ln2 over lambda, and that turns out to be 0.42 milliseconds. E1 positron emission tomography is uses a radioactive tracer. State what happens to the positrons emitted. So the positrons collide with the electrons and annihilate each other, and then these turn into gamma photons. Explain why a tracer with a half-life of approximately 2 hours is suitable to use. So with tracers, what happens is that when it's injected into the body, so it goes into a certain organ or a tissue where it starts to decay. And based off the radiations from the gamma photons we receive, we get an idea of the tracer concentration, which we use to build up the image. So it's long enough to build up the image, but it also does not unnecessarily expose the person to a lot of radiation. So it does not unnecessarily increase the radiation dosage. This is the last question. State what is meant by the luminosity of a star. So luminosity, this is again a textbook definition. Total power of radiation emitted. How standard candles are used to determine the distance to a galaxy. So standard candles are by definition objects for which you know its luminosity. And when you receive radiation from it at the earth, you know the radiant flux intensity. And then when you use the equation that links the two, L over 4 pi d square, so the distance from that star, from that galaxy can be found. The sun rotates on its axis. Points x, y, and z are on the equator of the sun as shown in 10.1. Now keep in mind that this diagram shows the sun and how it's rotating. So it's rotating in a direction like this. So this point goes behind and it comes like this. So it's in a direction like this. So it's rotating like this, right? Which is also shown here. Wavelength of lights from point x and y are observed and recorded in 10.1. So wavelength from x, wavelength from y is recorded. Now it's important to observe here that y is the axis of rotation. So if I think about circular motion, then I know that because it's at the axis of rotation, even though there is some omega value, because it's rotating, it has some time period, but because it is not at any distance from the axis by this equation, because r is 0, v also becomes 0, right? So this point is not really moving at all. And what we see is that the wavelength from x, that is more than this. The wavelength is more. And we are observing this from the Earth. So now if I just have to think about how this object is and where the Earth is in this diagram, so you need also a bit of visualization and a bit of 3D thinking. So I can say that the Earth could maybe be here, like in front of the sun, or maybe it could be at the back, right? Now if X is moving like this, we know X is rotating, so it would go behind and this part would then come in front, right? Now, if I see an increase in the observed wavelength by Doppler's effect, this means a reduced frequency. So this object is actually moving away from us. X is actually going away from the Earth. So then what I end up concluding is that the Earth is actually in front here and not at the back. Because if it was at the back, then X was moving towards that point, the frequency would be greater, the wavelength would be less. But that's not how it is. So the Earth is here at the front. All right? Okay. So now it says that the sun rotates with a period of this much, so that the radius of the sun is given by this value. So if the radius is what I need and I have the period, so I need the velocity, which I can get using this equation, this expression that you have, that V over C is approximately equal to delta lambda over lambda, or it's also delta F over F. So lambda that you have in the denominator is the original wavelength, which is this one. So for the one which is not moving, so that's in the denominator. So 656.2877 minus this divided by this, and C is the speed of light, 3 into 10 to the 8. So then you take it there and multiply. So this turns out to be 2102 meters per second. So I know its orbital speed now. And now if I know the orbital speed, I can just use this expression. V equals to 2 pi r over t. I need r, so that's Vt over 2 pi, and then I just plug in the values. And my answer turns out to be this. State and explain how the expected wavelength of light observed from Z compares with its emitted wavelength. Now, it's talking about light from Z. I already know that light from X is increased in wavelength. So light from Z must be reduced in wavelength, because if the Earth is at the center, so Z is actually moving towards the Earth. Right? Z is moving towards the Earth. So I can say that if Z is moving towards the Earth, so wavelength will be less, or you can say frequency would be more, so wavelength would be less. Part 3, luminosity of the sun is given. Use the information in B1 to calculate the surface temperature. So I know L, I have to find temperature, so I'll use the Stefan-Boltzmann law, 4 pi sigma r squared T4. R I also just found from this part here. So I just plug in the values. From rearranging you get T4, but then you'll also need to take the fourth root. How you can do this in your calculator is when you have, for example, T4 equals to this, and if you need T, so you can just raise this to the power of 1 by 4. I hope nobody gets stuck with this. So that temperature turns out to be 5770 Kelvin, and that wraps up this paper. So overall, this was a good paper. I wouldn't say the most difficult paper. In fact, in the light of some of the more recent ones, this actually appears a bit easier. So yeah, so hope this helped. Like this video, comment if you have any suggestions, or if you'd like to see something else. Share this with your friends who are appearing for the A2 physics exam soon, and subscribe to the channel for more cool content like this, because I assure you more cool content is going to drop soon. See you in the next video.